Okay, so we're going to start on chapter 8, which is about the preparation or synthesis of alkenes and their reactions. In the first part of this chapter, they discuss where you can get alkenes from, and there are a lot of naturally occurring alkenes in organisms, and because petroleum and coal are the products of the decomposition of organisms, well, there's still a lot of alkenes present in those materials. But, if you want to make a particular alkene or put a double bond in a particular place in a carbon skeleton, then we might want to know how to do that. And sometimes you need to do that so you can imitate a natural product or create a double bond in the midst of a pharmaceutical product, for example, or sometimes alkenes are the precursors to polymers. So there are a lot of times when we want to make a particular functional group in a particular place in a carbon skeleton. So some of what we're going to be talking about as we go through our study of various organic functional groups is how you make them, and in particular how you can get them into a particular part of a carbon skeleton. And we've talked in the earlier chapter about a type of reaction called elimination reactions. And that means to take out the elements of some small molecules normally. And we can do that to make an alkene. And we're going to see two examples in this chapter. One is called dehydrohalogenation, and the other is called dehydration. And these terms refer to what you took away from the substrate, which is the organic compound that we're going to operate on. And we're not going to really go into a lot of detail about the mechanism. We'll do that more in chapter 11. So we're really going to concentrate on what is happening and what are the possible outcomes of doing that. So we're going to start with dehydrohalogenation, and let's talk about that word for a second. The prefix D means to take away, and the hydro here is short for the hydrogen. Sometimes, you hear about hydroelectric power and you think hydro means water, but it does not in this case. And then halogenation or halogen is to take away a halogen. So we're taking away the elements of HX, and that's what this word means. And by X, we're going to normally be talking only about chlorine, bromine, or iodine. So I'm going to call those the common halogens in organic chemistry. Sometimes we'll talk about fluorine, but not very often. And HX is an acid, and you know that. And so if you wanted to remove or neutralize an acid, what would you use? And you have, a fair sense of this. If you just, sort of relax and admit it, you're going to probably say a base, which would be an excellent answer. So the next obvious question is, okay, so you need a base. So which base would you like to use? And again, I'm going to guess that the base of your choice is probably going to be sodium hydroxide. And that's okay. It's not soluble in organic solvents. And so usually we use KOH, but really the base is the hydroxide ion. So it doesn't really matter which one you pick. You're using the same strength base, and if you use KOH, it improves the solubility in the same solvents as the organic molecules are soluble. So that's normally what we use is KOH. But if you had said and thought sodium hydroxide, that's perfectly fine to think that. And the reason we have to worry about the organic solvent is because the substrate's not usually very soluble in water. So here's an example. So we have this alkyl halide. And remember, an alkyl halide means just a chunk of carbon, plain old sp3 CH bonds. It can be a chain, or it can be branched chain. It can be a ring that's not got any double bonds in it right now. It's just a plain old vanilla molecule. And it's got a halogen on it. And so we're going to put in our base, and remember I said we're going to use KOH. The alcohol here is a solvent, and we're going to heat it up some. That helps the reaction. So if we do that, we can get this product. And our side products, or the other things that come out of here, are KBr and water. Now, because we're organic chemists, we don't really care so much about those things, except to just know that they're there so we can get rid of them if we're having to purify this molecule. So this is called an elimination reaction, and we remove the elements of HBr. And so you notice that we don't make a molecule of HBr. The Br is a counter ion, an anion to the potassium. The potassium cation is merely a spectator. It's just there for the ride. And the OH picks up a proton off of the one of the carbons, and so the hydrogen off of this molecule and the bromine off of this molecule are ending up in these two different components. And let's talk about that now a little more obviously by numbering the carbons on this ring. And I've just numbered them starting at the carbon that has the bromine on it, because if we needed to, probably that's where we'd start. It doesn't really matter. We just want to know where things are on the ring. And so the next question is, okay, where did the hydrogen come from? And you're making a double bond, and so the idea here is that you're taking the hydrogen and the bromine off of adjacent carbons. So if you look over here, carbon number 6 and carbon number 2 are both adjacent to the carbon that has the bromine on it. And so when you look at this product, you know, when I asked you which carbon actually lost the hydrogen, you can't really tell the difference between number 2 and number 6. One of the things I sort of say tongue-in-cheek is, if you dropped this molecule on the floor and you picked it up, would you really know which one was originally number 2 and which one was originally number 6 if they didn't really have numbers on them? And you wouldn't be able to tell. So there's no difference between 2 and 6, but it doesn't matter. Either way, you're going to get a single product. And that's fine. That's pretty simple. And here's a drawing that sort of explodes out the hydrogen so you can see that. So one or the other of these red indicated hydrogens comes off to make the double bond. And if I put it here or if I put it here, I can't tell the difference. So I've put the numbers on there. Okay, so here's another example. Again, it's an alkyl halide. I've used bromine again. I could have used chlorine or iodine. It doesn't matter. And we put in the KOH, and so one of your first things is to recognize that this is a base, and so you're looking over here to see where there might be an acid, and it's going to turn out to be a hydrogen that's not too far from this bromine because of electronegativity influences. Remember the tug-of-war argument. So that's why the hydrogens are acidic enough for this to get started. And like I said, we'll talk a little bit more detail about the mechanism in a later chapter. But if we number the carbons again so that we can talk about it, again, it doesn't matter where you start, but just number all the carbons so we can say which carbon or carbons can lose a hydrogen in this reaction to make a double bond. And it's going to have to be one of the ones that's adjacent to the carbon, which in this case I've numbered number 3. So adjacent to that carbon, I can look to number 4 or I can look to number 2, and both of those have hydrogens on them. So either one could be the one that loses the hydrogen. But are they the same? Or another thing to ask would be, if I take a hydrogen off of number 2, do I get the same product as if I take the hydrogen off of number 4? And the answer is no. They are different. Number 2 is a tertiary carbon. Number 4 is a secondary carbon. So right there you can tell there's a difference. They look different in the skeleton. So let's draw some pictures and see how those two products look. So if we took away a hydrogen off of number 2 and the bromine from number 3, we would get this product. Or, so I put the numbers on there so you can kind of see that. Or if we take away the hydrogen from number 4 and the bromine from number 3, and we get this product. And again, here's the numbers to sort of help you keep track of that. Okay, so now we have these two products. And now there's another question. Are these products both equally likely to form? And to answer that question, we have to decide, are they the same? Well, they're not the same. And so if they're not the same, do they have different characteristics, different properties? Is there a different amount of energy that you're going to get out of one of these reactions products versus making the other. They come from the same starting material. In other words, we're talking about thermodynamics, which one would produce the most enthalpy, and that one should be the most favored. And here's where our discussion about the patterns of substitution around the double bond comes into play. So, how substituted is the double bond in this molecule? And what do? You look to see how many hydrogens are missing from the parent ethylene. So this one has 1 hydrogen and 3 carbons, so this one is tri-substituted. And this one is di-substituted, and the way I've drawn it here is trans. And so the major product is going to be the more substituted alkene, because remember we talked about the order of stability. Tri-substituted is more stable than di-substituted, all of the di-substituted ones. Now one thing you might pick up on is I drew this as trans, and what if it were cis, but it's still going to be minor compared to the tri-substituted one, and we're just not going to get too bogged down in whether it's cis or trans. Now there's a similar reaction that we can use called dehydration, and this is, again, the terminology is removal of hydration. And hydration is moisture, so the loss of moisture, the loss of water from an alcohol. So we call that dehydration, and water and alcohols are very similar. And so if you're trying to get an OH out of something, and you're trying to do it in such a way as you take away a water molecule, well, what's the other thing that you need? You might be able to figure this out if you think about it for a few minutes. If you've got an OH on 1 carbon and you're trying to make that into a water molecule, well, you need another hydrogen, right? In the form of a proton. Well, where do you get protons? Well, think about it. That's from an acid. Okay? So, if you start thinking of acids, you remember the acids from general chemistry. You have HCl and HBr and HI, nitric acid and sulfuric acid and so on. It turns out that for this kind of process, we're going to try to avoid the HX molecules, HBr, HCl, and HI, because the halogen anions might get involved doing something else that we don't want. And we'll go into more details about that later. Sulfuric acid is a good choice, or phosphoric acid, because their anions are not going to do anything. They're not going to cause any side reactions, any other possible outcomes. We say that their anions are non-nucleophilic. And as I said, we'll get more into details about what that really means in another chapter. But either one of those is a good choice. And in industry, they use both of those, sulfuric acid or phosphoric acid, either one. And either one would work fine in a lab as well. So here's an example. Again, I started out with just a simple molecule that's an alcohol. And so what we're going to write here is the acid in aqueous solution, and we're going to heat this one up too. Again, not a whole lot of heat, but just heat it up a little bit. And what are we doing? We're looking for where might the double bond be able to go. And it's going to have to go between the carbon that right now has the OH on it and an adjacent carbon. And so we're going to number the carbons again so we can talk about it. So I've just numbered everything. This is not, for nomenclature purposes. But if you look at this, again, I can't really tell the difference between carbon number 2 and 5. But they both have hydrogens on them, and so I could put a double bond here or here, and it would be the same thing. But I also have hydrogen out here, and that carbon is also adjacent to number 1. And if I take a hydrogen off there, I'm going to get something different, and that's how I get this molecule over here. So then the next obvious question is, okay, are these two molecules the same in stability? And so we have to again analyze them the way we did before, which is to think about how substituted are these double bonds. So, how substituted is the first molecule? This one is tri-substituted. And this one is di-substituted and terminal. Well, which one of those is more stable? Well, again, tri-substituted is more stable, so that's going to be the major product. The thermodynamics are going to favor making more of that because it's more stable. You're going to get more energy released from that reaction product. Whereas this one is less substituted. That's going to be a minor product. You notice that I haven't said this is the only product we're getting a mixture, and there's not a whole lot you can do about it. At least not with these example of elimination reactions. We can't really keep the mixtures from occurring. Alright, so far what you need to be able to do is you need to be able to recognize which reaction conditions and products work for dehydrohalogenation and dehydration reactions. In other words, if you have an alkyl halide, you got to remember you use a base to cause that elimination reaction, the removal of HX. And if you have an alcohol, then you use an acid like sulfuric acid to cause the elimination dehydration reaction on that. You need to be able to either pick out or draw the products that are possible from such reactions. And I'm going to stop with this portion of the chapter.